Hello, this is the second video lecture in ECON320, and today we're going to talk about consumer choice. Today's lecture will closely follow chapter 4 of Van Prince, the theory of individual behavior, and if you're interested in this topic, the additional readings will be chapters 3 and 2 in Varian, posted on Moodle. Before we begin, a quick one-slide recap of what was covered in the previous video. In the previous video, I introduced the basic framework for decision-making, the theory of rational choice, and it basically says the following. There are two components of choice, preferences and opportunities, and if preferences are complete and transitive, then we can use a utility function to describe them. We can create a numeric representation of those preferences, and the opportunities basically add a feasibility constraint on the choice. And the decision rule that a rational agent should follow is to pick the best alternative of the available alternatives, that is, maximize utility subject to the feasibility constraint. Today we're going to add more muscle to the bone by specifying what kind of preferences a consumer should have and what kind of feasibility constraint the consumer is facing. So today we're going to look at a very specific case of rational choice, that is consumer choice decisions with respect to consumption. So when we switch to consumer choice, let's talk about the model assumptions first. For once, we're only going to focus on a world in which there are two goods to choose from. We'll call them goods X and Y. The sets of alternatives in this world would be all possible consumption bundles of these goods. For example, I can say one alternative A would be 5 units of X, 3 units of Y. Alternative B could be 2.4 units of good X, 2 units of Y, and so on. So think about all possible combinations of some amount of good X, some amount of good Y. That would be an alternative. We will, of course, assume that the consumer's preferences are complete and transitive so that we can describe them with the utility function, and that thus each consumption bundle can get a utility label associated with it. In addition to preferences being complete and transitive, we would also like the preferences to be such that more is always better. So for example, in our case, the bundle A should always be preferred to bundle B because it has more of both X, 5 versus 2.4, and Y, 3 versus 2. So A should always be preferred to B, no matter how much more the consumer likes X or Y. And the second additional assumption is that the marginal utility of consumption should be decreasing. That means that the consumer always likes more of some good, but each additional unit of a good will increase utility at a decreasing rate. The first unit of X will be more valuable to the consumer than the second unit of X will be more valuable to the consumer than the third, and so on, and same for Y. So these are two additional assumptions. More is always better, and marginal utility is decreasing. That will shape the way the utilities look in this world. And so if we want to look at the graphical representation of preferences, we can think of a plane representing all possible consumption bundles. So we're gonna put the amount of good X on the horizontal axis, we'll put the amount of Y on the vertical axis, and each consumption bundle would be just a point in this plane. For example, bundle A that I talked about today already, 5 units of X, 3 units of Y, can be represented by a point with the horizontal coordinate 5 and the vertical coordinate 3. Given the assumption that more is better, all bundles in the blue regions will definitely be better than A because they will contain more of both goods. And on the border, of course, it's going to be more of one good and the same of the other, so it's still going to be better. Similarly, the bundles in the red region right here will be worse because they will contain less of at least one good. So this additional assumption allows us to say that, well, no matter whether the consumer likes X a lot more than Y, blue region will be preferred to bundle A. Any bundle in the red region would be worse than bundle A. So if we ask consumer, what kind of bundles do you like the same way as A? Those would be bundles with either more of X and less of Y, so in the bottom right white region, or bundles with less of X and more of Y. And let's add several of such bundles in the picture. So suppose that the consumer is indifferent between all these 5 bundles, A, B, C, D, and E. Indifference means same utility. So if we were to plot all possible bundles that have the same utility, we can connect them by a curve, and that curve is called the indifference curve. So here, the 5 bundles that I've talked about are just examples of bundles that the consumer is indifferent between, and all such bundles will lie on the same curve. So an indifference curve captures all bundles that have the same utility. And so if we variate utility, we can get various different indifference curves. So going back to the original set of all alternatives, we basically can split that set into a collection of indifference curves. And each indifference curve will stand for a particular utility level. So clearly, the farther away we move from the origin, the higher the utility is going to be because more is always better. So this is basically the idea of preferences. We'll represent them by indifference curve. An important property of the indifference curve is that each curve must be convex because of the decrease in marginal utility of the consumption. And here's the example in this story. Suppose that we're currently at point A, consuming 5 units of X and 3 units of Y. And suppose we're going to reduce the consumption of X by 1. To stay on the same indifference curve, we need to be compensated by higher consumption of Y. And suppose by going from 5X to 4X, it's good enough to be compensated with 2 units of Y. But then if we wanted to reduce the consumption of X by 1 more unit, we need to be compensated by way more than just 2 units of Y. Because marginal utility of consumption is decreasing, giving up the 4th unit of X is more valuable than giving up the 5th unit of X. So you need to get more in return in order to stay on the same indifference curve for the 4th unit rather than the 5th unit. And that results in the convex bowed out shape of the indifference curves. You can also think of the slope of the indifference curve as the marginal rate of substitution. Of course, keeping in mind that it's negative. So formally, the negative of the slope of the indifference curve is the marginal rate of substitution. And you can calculate it by just using the regular rise over run equation. So I'm gonna find the approximate slope between B and C and approximate slope between A and B. And you can see that when we move from 5x to 4x, we trade it for 2 units of Y, so the marginal rate of substitution is going to be 2. But when we move from 4 units of X to 3 units of X, we trade this 4th unit of X for 6 units of Y, so the marginal rate of substitution here is going to be 6. So marginal rate of substitution will be high when you have a small amount of X and a lot of Y. You care a lot about X in that case, you don't care much about Y, but as you increase the consumption of X, each additional unit of X will be worth less and less and less in terms of Y, so the slope has to fall in absolute terms. And this gives you the U-shaped convex form for the indifference curve. Now that we've described the preferences, let's talk about the feasibility constraint. And when it comes to consumption, we'll call it a budget constraint. And so the standard assumption here is that the consumer has particular income, $M, and he's facing fixed prices. So he's a price taker, or she is a price taker in this world. The prices are px for 1 unit of x and py for 1 unit of y. And so any bundle of goods x and y that costs no more than $M is feasible. So you can think about a situation when you go to a grocery store and you have a particular amount of money in your pocket and you're seeing the prices in the grocery store and you can't bargain. So you just need to decide what to buy given how much money you have. Or think about going to a restaurant and again, fixed amount of money, you have a menu in front of you and you need to decide what you want to have. So formally, the restriction on the cost of the bundle can be written this way. Px times x is the amount you will spend on x units of good x. Py times y is the amount you will spend on y units of the second good y. So the total cost, the total amount that you spend on the two goods may not exceed the total amount of money that you have. And this is the inequality constraint that determines what you can and what you can't buy. In addition to that, we'll call the equation, so if we replace the inequality sign with the equal sign, we'll get an equation. Price of x times amount of x plus price of y times amount of y equals income will be called the budget line. So the budget line describes all bundles that cost exactly the amount of money that you have to spend. And so let's look at the graphical representation of the budget constraint. Again, we're back in the world of two goods, and so x is the horizontal axis, amount of good y goes on the vertical axis. And so let's work out a simple example. Suppose that you have $200 to spend, price of x is $25 and price of y is $10. First off, let's write down the budget constraint. The budget constraint says that 25 times the amount of good x plus 10 times the amount of good y has to equal to 200. This is the budget line. 25x plus 10y is 200. Let's draw that budget line. If you're only gonna spend all your income on good y, then $200 at $10 a piece will buy you up to 20 units of good y. So the maximum of y that you can get is 20. Similarly, if you're only gonna spend all your money on good x, $200 at $25 per unit will buy you up to 8 units of x. So these are 20 and 8 are the maximum amounts of y and x correspondingly that you can purchase. Now, if you connect these two points with a line, you'll get the budget line. So the easy way to construct it is by looking at consumption bundles that have only one good in them, only y or only x. And so the budget line carves out a triangle in our consumption space, and that triangle will be called the budget set. Bundles exactly on the budget line cost exactly $200. Bundles inside the blue triangle cost less than $200 and thus are still feasible. Technically, you can get any bundle inside the triangle and there will be some money left. Bundles outside the triangle cost more than $200 and you cannot afford them. They're infeasible. So the feasibility constraint here is given the amount of money and the price of two goods, you'll get a particular triangle, the budget set, within which you can make decisions. The important property of the budget line here is that its slope is equal to the negative of the ratio of the two prices, with x going on top and y going on the bottom. So when the price of x is 25 and price of y is 10, the ratio is 2.5, so the slope of the budget line at every point is negative 2.5. Now let's summarize. When it comes to consumer choice, preferences can be summarized by indifference curves, which are U-shaped because of the decreasing marginal rate of substitution or because of decreasing marginal utility of consumption. The opportunities are described by a budget set, which in the simplest setup is just a triangle. And so a rational consumer should choose the best feasible alternative. So this is, again, the optimal decision rule applied to this situation. Now we can get more mileage out of this last sentence if we actually look at what's going on when we put preferences and opportunities on the same picture. So again, the blue triangle is the set of feasible bundles given the amount of money that you have and the prices, and the red lines represent your preferences in the sense that all bundles on the same red line have the same utility. And the indifference curve farther away from the origin has higher utility. So this indifference curve has the lowest, second lowest, and the highest. And so your goal as the decision maker is to find the bundle inside or on the boundary of this triangle that sits on the farthest, on the indifference curve that is the farthest from the origin. And so you can guess that the first two indifference curves will not be the optimal indifference curves because you can move even farther. But you can't go as far as the third indifference curve because it is completely outside of the budget set. So intuitively, there should be some indifference curve that's just touching the border of the budget set in just one point. And here's an example of such an indifference curve. And the point of tangency I'm going to call point A. And try to convince yourself that point A is in fact the optimal choice in this situation. A guarantees you the highest utility level, the farthest indifference curve that you can get while staying in the budget set. If you don't get tangency, then probably there is some other indifference curve that's still attainable. So tangency means, well, you can't go farther without leaving the budget set, and at the same time, you can get more by moving along the budget set in either direction either. So here's an interesting property. A is the optimal point, and in the optimal point, when the utility is maximized inside and on the boundary of the budget set, first of all income has to be spent. In this story, we only get utility from consuming good X and good Y, so there is no point in leaving the grocery store with money left in your pocket. You should spend all your money and in a way that maximizes your utility. The second interesting observation is that the slopes of the indifference curve on which point A lives and the budget line have to be the same. That is, the marginal rate of substitution at point A has to be exactly equal to the price ratio. So whenever the price ratio changes, the optimal point should change as well. I guess in a nutshell, this is all that I wanted to convey about consumer choice. So try to remember this picture with the indifference curve being tangent to the budget line. And in the next video, I will talk about how this picture, this optimal consumer choice model, can be used to derive an individual demand function. Thank you.